Today we're going to be taking a look at a Kubernetes capability that is quite new, but it's also been around for a while, and it's called Gateway API. It has only started getting traction over the last couple of weeks. What is Gateway API? Why does it even exist? What are the features? So what can we achieve using Gateway API? How to deploy it and how to use it. This video is the first video that is part of a mini series on Gateway API. So in this video, we'll take a look at the features and capabilities, but at the end of this video, I'll provide you some links to material to other Gateway API controllers that I want to cover in the series. So this is why you should subscribe. So if you like the video, be sure to like, subscribe, hit the bell so you know when the next episode drops. Let's get straight to the point, so without further ado, let's go. So looking at the Kubernetes documentation, Gateway API is basically just a family of APIs, similar to how Ingress is an API that Ingress controllers use. Gateway API is a set of APIs that Gateway API controllers can use. So it's a set of APIs that make network services available, and it does so by using extensible, role-oriented, protocol-aware configuration mechanisms. Basically, what that allows us to do is to achieve advanced traffic routing. Gateway API solves a bunch of challenges that Ingress had. So think of Gateway API as a more advanced Ingress. Instead of defining absolutely everything in one Ingress rule, we can now build routing rules in modular fashions. So if you're familiar with Ingress, Ingress is one rule that defines how does traffic come in, what to do with the traffic, all in one object. Gateway API is similar, but it's role-oriented. So it allows us to model our traffic after organizational roles that are responsible for managing Kubernetes and service networking. So think about a large enterprise company. You have infrastructure people, you have cluster operators, people who are in charge of Kubernetes, and then you have application developers. So different people interfacing with the platforms in different ways. Then you have application developers, and all their concern is about running applications in the cluster, pretty much writing code and having their applications run in the cluster. So firstly, Gateway API allows for a portable specification. This means we can move Gateway API between different controllers, so we don't get vendor locked. It's also quite expressive. That way we can expressively specify what to do with the traffic, similar to what we could have done at Ingress, but more modularly. And Gateway API is also very much extensible. For example, application developers should only be concerned with how their application receives traffic. So developers more like, I want this domain and this path to come to my service. They shouldn't be concerned with what TLS certificates are being used, how it's rotated, what networking ports are used, and how the operating system load balances the traffic. That's more for the cluster operators. The same way cluster operators shouldn't have to be concerned about how the cloud infrastructure provides the traffic to the cluster. Their concern is more about the network traffic, the security, the policies, what ports are used, how it's load balanced. Same way the cloud providers or the infrastructure folks shouldn't be concerned what network policies are used within the cluster. They're more likely to take care of things like what AWS load balancing capability do we provide to the platform? Do we use a API gateway in AWS? Do we use an ALB, an NLB, an Azure load balancer, or an API gateway? Gateway API achieves this separation by having a resource model that is modeled around this. So these are the main concepts you should understand when looking at Gateway API. First of all, the gateway class. What is a gateway class? So gateway class defines a set of gateways with a common configuration that's managed by a controller. Think about in the Ingress world, you might have an HA proxy Ingress controller, you might have an Nginx Ingress controller, and you use an Ingress class that distinguish which Ingress controller takes care of which ingresses. The same way, Gateway API has a gateway class that defines that. So we could have a gateway class that says these gateways are used by Istio or Traffic or Envoy. This is the highest level API, and it's defined globally within the cluster. It doesn't sit in a namespace. The next object lives in a namespace, and that is the gateway. The gateway defines an instance of traffic handling infrastructure such as a cloud load balancer. So the gateway could point to something like an API gateway controller like Istio, Envoy, Cilium, and more. It also helps define things like a cloud load balancer. So if you're running an Azure, how do we want to manage that Azure load balancer? The gateway lives at a namespace level. This is the power of this whole thing. It's all modular. So I can say a specific department uses a specific gateway. Another department might use a different gateway. This way we can split things up. Then we have our routes. Now the popular ones are HTTP route and gRPC route. This is kind of like the rules we have within an ingress, where you define HTTP specific rules for mapping traffic from a gateway listener to a back-end endpoint like a Kubernetes service. So developers would be concerned with HTTP routes because they can say, I want this domain and this path to come to my service A. So this is how I like to visualize this modularity in action. So you have a Kubernetes cluster, and at the top here, this is your public domain. Traffic comes in from a client and it goes to what's called the gateway. Now cluster operators look at this gateway. The gateway will define what ports are exposed, 80 or 443. It also points to things like TLS certificates you can see over here. And these TLS certificates can live in different namespaces, so they're decoupled from the actual gateway. This is great for security. And then we have the gateway class managed by infrastructure operators, and this defines the implementation. What implementation is available to our cluster? So this will define things like, do we use a traffic gateway API, an Istio one, or whichever product it uses under the hood. That is implemented by the gateway itself. Gateways can live in any namespace, and they basically forward the traffic based on HTTP routes. We have HTTP, gRPC, TCP, and UDP, and there are more routes to come. Then over here we have application developers, and they basically define the routes. This defines HTTP like specific rules that map the traffic from the gateway to the upstream service, which then goes to pods. We can also see this model explained on the Gateway API Special Interest Group documentation, where they explain all of this in detail. So you have infra providers taking care of gateway classes, cluster operators looking after gateways, application developers managing their routes. So to take Gateway API for a spin, we'll need a Kubernetes cluster, and for that I like to use a utility called Kind, which allows me to create lightweight Kubernetes clusters that I can use for testing. In this video I'm going to be using Kubernetes 1.34. After that is done, I check my cluster and we're good to go. To start working with Gateway API, we have to install the Gateway API CRDs. At the time of this recording, the CRDs are not part of the native Kubernetes installation. So unlike things like ingress and config maps and services, Gateway API has to be installed in the cluster. And we can grab this off the Gateway API Special Interest Group documentation. There is a standard channel, which you can just apply using kubectl, or the experimental channel, which you can apply using kubectl. Now, given this is an informative video, I want to show you all the possible features. So in this video, I'm going to be using the experimental channel, something you want to keep in mind before going to production. So I simply kubectl apply the experimental channel release, and in this video I'm using 1.4. I go ahead and install that on my cluster. And you'll see that this applies a bunch of new objects to the cluster. So there's gateway class, there's gateway, HTTP routes, and some other routes and features. Important to know that this list will constantly evolve and change, as Gateway API is evolving and changing rapidly. And as you can see here at the time of this recording, the stable channel gives you gateway class, a gateway, and HTTP route. You can retrieve these using kubectl. The experimental channel has things like TLS route, TCP route, and UDP route, and more. Important to note that the Gateway API is extremely new, so a lot of the stuff I say in this video might be irrelevant in a few weeks' time. Things like CORS and OAuth and external authentication. These are all coming into the experimental channel. Now that we have a Kubernetes cluster and we have the Gateway API CRDs, we can go ahead and install a gateway class and a gateway. We can set these up and we can then decide what Gateway API implementation we want to use. Now this video is all about Gateway API and does not concern the implementation. So whether you decide to use Istio, Envoy, Traffic, Cilium, it doesn't really matter. Everything you see in this video should technically be supported by all the controllers as it's a default standard. We will then deep dive each of the specific controllers in future videos. So in this video, I just randomly picked a popular Gateway API controller that's easy to install. In this example, it'll be Traffic. So I just give the chart a version, I say Helm repo add, I add the Traffic Helm repo. I can then also search for other versions if I want to. And after running that in my terminal, I simply say Helm install, and I go ahead and install a basic Traffic API Gateway controller. I paste that to my terminal and we get our controller deployed. I can then go ahead and check my installation by running kubectl get pods. Go ahead and run that and that's all looking good. I can use the kubectl logs command to check the output if my controller is happy. We can see that it's there, it's all good to go. And since we don't have a load balancer, we're running kind, we're just going to use port forward to create a endpoint that we can start to use. So kubectl port forward is great for that. I go to my terminal and I set that up, and I can leave this terminal running in the background somewhere. For testing and evaluation purposes, load balancers should not concern us. Port forwarding is great for this. You don't need some open source load balancer to test and trial out things. Same way, we're going to need a DNS endpoint or a domain. And for that and local testing, I just like to use a host file. We can use a simple host file entry to set up some example domains. So I'm going to have one domain called exampleapp.com, another one specific to a service like a Go service or some kind of functionality you want to expose, and another one for another API like exampleapp-python.com. Windows and Linux both have this feature. In Windows, you can find it in the System32 drivers etc directory. In Linux, it's in etc hosts. Once you've saved that, you'll now have a domain or a DNS entry that you can test with locally. And we point this to localhost because that's where we're running our port forward from. So all the traffic here will go to our Gateway API controller. Next up, to fully evaluate these features, we're going to need some example applications. So we'll need something like a Go microservice that we can run, and maybe a Python one to simulate different technologies. And in the real world, you also want a front end, something written in HTML that perhaps makes an AJAX post call to one of the back end services. To do this, it's really straightforward. I have a bunch of example apps that I use throughout my videos. So in my Git repo, I have a Python folder with a deployment YAML. I have a Golang folder with a deployment YAML. So this will deploy a Go and a Python microservice. And then I have a webapp.yaml, which is a simple web HTML, which makes a post call to the backend API, the Go application. Very easy to get this running. I just copy paste this, jump into my terminal and paste it. With that deployed, I can now say kubectl get pods, and we have two instances of our Go service, two instances of our Python service, and our web front end. Also important to notice, all of these services have endpoints that are not exposed. They're all cluster IP, so they're all just running locally and privately and securely within our cluster. Gateway API is all about making these applications publicly accessible, similar to an ingress. Now, how do we send traffic to these example applications? Firstly, we need to take a look at a gateway class. Now, the gateway class is a Kubernetes object we'll define in YAML that the infrastructure providers look at. The first point of call of traffic into our cluster will be via some sort of load balancer. If you're running an EKS or AKS or GKE, you'll have a public endpoint. That public endpoint is provided by some sort of hardware or infrastructure. So infrastructure people should provide you this capability. And that is what a gateway class defines. It basically says, what implementation are we going to use to accept this traffic? So we'll go ahead and install a gateway class. Now, a gateway class is a cluster scoped resource, so it doesn't live in a namespace, and it's provided by the infrastructure guys. This resource presents a class of gateways that can be instantiated and used. So installing a gateway class is as simple as applying a small YAML file. Now, because in this example I'll be using traffic, my gateway class specifies that my implementation of my gateways will be traffic. And this is what a typical gateway class looks like. You give it a name, you can call it anything you like, it lives at a cluster level, and it points to a controller, which is the implementation that will be implementing this gateway class. You can have a few of these running in your cluster. So it's as easy as grabbing this YAML file and applying it to your cluster with kubectl. Then just like any other Kubernetes resource, we need to test to make sure it's working. We say get gateway class, you can see it's there. And like any other Kubernetes object, you want to describe it to make sure it's functional. And what you're looking for here is the status. Make sure that it has been handled and it is accepted and that there are no errors here. This actually means that my controller behind the scene that we deployed with Helm has actually gone ahead and handled this and accepted it. If there's any problems here, your traffic will not work and will not be accepted to your pods. So kubectl describe, always check whether your class is successfully implemented and accepted. Now we have a gateway class deployed to our cluster, so our infrastructure team has given us load balancing capabilities, and now our cluster operators can define how we want to accept traffic into the cluster. What ports do we want to expose? What TLS certificates do we want to use? This is all done using a gateway. We can have a gateway that attaches to the traffic gateway class. We could have another gateway that attaches itself to an Istio gateway class. So it gives us this flexibility. Now, typically the gateway lives in the same namespace as the routes and applications, but it does not need to. This gives you even more flexibility, as you can have a gateway per namespace. You can have a central gateway, which allows all routes to attach to it. That's a lot of power and flexibility. And you can protect all of these resources using general Kubernetes RBAC. Same way I applied a gateway class, I can apply a gateway using a simple YAML file. And this is what a gateway YAML looks like. You can give it a name, so I can either call it something like traffic, so people know it's a traffic gateway API, or I can give it a generic name, so I hide the implementation from developers. This is all up to you. I'm just going to deploy it in the default namespace. So this is my gateway that will manage all the traffic coming into my cluster, and I bind this to my class by using this gateway class field. This gateway will then implement this gateway class. Next up, we want to define how is traffic coming into the cluster. We do this setting up listeners. You can have multiple listeners. This is an array, so we can have a rule for HTTP and HTTPS. I like to expose HTTP because I can use this for health probes. Health probes for the load balancer, health probes for specific endpoints, and I can set up a rule, and we can always redirect non-HTTP traffic to HTTPS. So here you can see what I've done is I have an entry for HTTP. This is the protocol and the port. And then this is the next modular capability that I like, is that you can say what routes are allowed to attach to this listener. So I can say only routes from the same namespace as this gateway. So in this case, because I deploy this gateway to the default namespace, only applications in the default namespace can use this gateway. I can also change this to say all. Basically, then I can move this gateway to a more like a platform engineering specific namespace, or something like Kube System, or wherever you're centrally managing things. And that means that all HTTP routes and general routes can be attached to this gateway. Or you could use something like a label selector. That's also really useful. This allows you to totally customize what routes can be used on this gateway. And the HTTPS one is pretty much the same. The only difference is that I can do things like say TLS, and I can say turn on TLS and the mode is terminate. So this allows me to terminate TLS at the gateway level and then route to different ports on upstream services. And this is also the magic that I like, is you can give a certificate reference, and the certificate reference takes in a namespace as well. So this is a secret in the default namespace for TLS. This means I can put my TLS certificate anywhere in my cluster I like, and the gateway will be able to read it. This also means that I don't need a TLS certificate in every namespace. I can centrally move it to one place. I can use RBAC to protect it and only allow cluster operators to rotate it, and they don't have to rotate many certificates. You could also use something like Cert Manager to rotate it. And again, it also has the same settings like allowed routes. So this is how we set up a simple 2 listeners, one for HTTP and one for HTTPS. And keep in mind that this is a standard implementation, so it doesn't matter what gateway API controller you choose. This should be implemented and working across all of them. Then I jump to my terminal and I go ahead and apply that gateway. Then I can do kubectl get gateway. We can see it's there in our default namespace. Remember, gateways are namespaced. I can then say kubectl describe gateway, and we can look at the status, and it is accepted and valid. But notice that I do have an error on one of my routes. So the first one doesn't have an error, but if we scroll down, we can see there's an error because our TLS certificate is not found. I have not gone ahead and installed a TLS certificate just yet. In this video, I'll be using a self-signed local certificate once we take a look at TLS. But our gateway is good to go for now. Next up, we're going to take a look at some real-world traffic examples. Now that we have our infrastructure in place, we can go ahead and use gateway APIs from a development standpoint. Let's take a look at some real-world functionality. The most important one I want to cover from an introduction standpoint is the traffic management features, which features HTTP routes. And there are some important fields on HTTP routes that we'll cover, such as parent ref, section name, host names, rules, matches, and filters. We can use this to construct rules for what to do with the traffic coming in via our gateway. Now, the first most basic, simplest example is routing traffic by host name. If you have an application like example app Go and you want to send that to a Go service, you have multiple departments all have their own DNS or domain names, and you want to route based on host. We do this with ingress controllers and any kind of reverse proxy by inspecting the traffic and looking at the host header, and this allows us to route based on host header. So what we can do is we can set up something like example app.python.com, go to Python service on a different port, and we can have another domain like example app.go.com route to a Go service. So this is basically an HTTP route routing to an upstream Kubernetes service. So that is the Kubernetes service port that we're mapping there. And because we're running a local domain using our host file, we'll be able to access these on our browser. So let's look at our first rule, which is an HTTP route by host name. And this is how you define an HTTP route. You give it a name and a namespace. This is our Python route. I'm going to be showing you 2 routes within the same file. The first field we want is parent refs. This helps us define what gateway to bind to. And here we are pointing to the Gateway API gateway that we created earlier. Gateway API also allows us to bind to a specific listener in the gateway. So remember, our gateway had an HTTP and an HTTPS listener. So in this example, I'm showing you how to bind to a specific listener using the section name. And this is the type of object we want to bind to. In our case, it's called a gateway. And then I specify what host name do we expect for this traffic. So this is example app-python.com, and then we can specify what we want to do with this traffic using what's called rules. Rules is an array, so you can have multiple rules, and we'll look at more complicated ones as we go along. Here we don't really have much rules other than the fact that we want all traffic to go to the Python service. So we create this thing called a backend reference, and this points to a Kubernetes service. The Kubernetes service name is Python SVC. It's running on port 5000, and we can give it a weight. So this means we could have multiple rules, sending maybe 50% of traffic to one and it's 50% of traffic to another. And then I've got the same one here, but this time for a Go service. So HTTP route, we give it a name and a namespace. We bind to the Gateway API over here. This is our host name. This time it's example app-go.com, and a backend reference, this time pointing to the Go service on port 5000. I can hop into my terminal, kubectl apply that, and immediately these routes will be created. They'll be consumed by our Gateway API controller, and they should be accessible. So using these links, we can go ahead and access our Python and our Go service. Here you can see we have hello from Python and we have hello from Go. So this is how you route traffic based on domain. Next up, you can route traffic based on path, and you can do this in a number of different ways. You can configure the path that's coming in to your platform, as well as the path that is passed through to the upstream service. So to do routing by path, we can do so using different strategies depending on what we want to achieve as the outcome. We can do exact match of the path. This means anything with just slash goes as it is to the upstream. In many cases, using exact is not really useful because if we define an exact path as slash, that means the upstream will not be able to accept any other paths or files behind it. We can do path prefix, so we can say anything slash star goes to upstream slash star, and this is very much a more common approach. And to achieve pathing by route, let's take a look at an HTTP route that does so. We're going to override the route we had before, so use the same name, bind to the same gateway, have the same host name, but this time our rule is a little bit more complex. This time we're adding a match section by path, and here we say exact. So technically, this will only allow us to visit the path slash. And then whatever matches this path will be sent to the upstream service. Whatever doesn't match this path will hit the 404 default page of the Gateway API controller. It's important to understand when debugging this, make sure you know what 404 you're hitting. Sometimes developers can get confused because their path gets a 404, but it may be the 404 of the upstream instead of 404 of the gateway. So just be mindful of that. Then we're going to do the same for the Go service. So HTTP route, the name and namespace, we bind to the same gateway, we use the same host name, and here we also use an exact path. So let's see how that behaves. Go ahead and update that. Head over to our URLs, press enter, we see no difference. On the Go side also, we see no difference. But notice I have a status endpoint on my Go service, and if I hit that, I get page not found. But I do know that my Go service does have a status endpoint, but this is because we used exact match. We're only matching exactly the path slash and sending that to the upstream Go service. In this case, slash status doesn't match. It doesn't match the exact rules, so it's not going to go to the upstream. It's going to get a 404 directly from the Gateway API. If we wanted all of the paths to be servable from the upstream, we can change the type to path prefix. This will pretty much match and allow us to visit slash star, so anything behind the slash, and pass the entire URL to the upstream. So if I go ahead and apply that, again, go to my path and refresh, you can see it immediately returns okay. So now anything I pass as a URL will go to my Go service. This is useful if you have services that have their own dedicated domain. There are, however, scenarios where services are sharing a domain, like you might have a central api.example.com domain, which routes paths to different upstream microservices depending on the path. We can do this type of routing using URL rewrite. For example, we can rewrite host names or URLs using the URL rewrite feature. So we can merge our APIs under one domain. So I can use example app.com and I can say /API/Python, go to the Python service. Note here that my Python service does not see the URL portion API/Python. So anything behind the Python syntax here will go to the Python service, but nothing in front. The same way for the Go service, everything after API/Go goes to the Go microservice. This means we can do /API/Go/status, and status will be passed to the upstream service like so. So we are rewriting the prefix here. And this is fairly straightforward to do with an HTTP route. So let's go ahead and update our routes for our Python and our Go service. This time I'm going to change things slightly. So we still have the same name and namespace, still binding to the same Gateway API. This time I'm changing the host name. I want to run my Go and Python microservice behind a central example app.com domain. And here I'm going to specify a rule. This is a slightly more complex rule, but it's still very simple. So this time we match on a specific path API/Python. But the key word here is that we want the type of match to be a path prefix. This means that technically we could have anything behind this path. Then what we do is we're going to apply a filter, and this is where the type is URL rewrite. This is the module we want to use provided by the Gateway API specification. And each of these types generally have different settings things underneath. So you can have types like dealing with CORS, dealing with upstream authentication, and other types that are still coming in the experimental channel, some that are GA, and more to be implemented in the future. So this is a rapidly changing ecosystem. And what we're going to do here is we're going to pass some parameters to the URL rewrite module. It needs a path, so it needs to know what do we want to send it to. In our case, we want to replace the prefix match. So here we have a path prefix API/Python. We want to replace it with /. That means that the upstream service, in our case the Python service, will not see API/Python as part of the URL. It'll only see what's after this prefix. So this is really useful. You can see it in action when we start taking a look at the Go service, because the Go service also looks the same gateway API, but also the same domain. So it now shares the domain of the Python service, and it has its own different match rule to say /API/Go as a path prefix, and URL rewrite that and change that prefix to /. So don't pass API/Go to the upstream Go service that we have over here. So let's go ahead and apply that and see what it looks like. Now this time I can open up API Python or API Go. If I do so, you can see API Python goes to the root page of the Python application. Notice if I do /status on this one, I get a not found, and this time this is the not found of the Python application. So here our gateway API is passing everything after API/Python to the upstream service, and the Python application doesn't have a status page. So this is a classic example of understanding where your 404s is coming from. So here our gateway API is working as expected. We can do the same with the Go service. See /API/Go goes to the Go microservice, but our Go service does have a status page. So I can go /status and we can see that goes to our Go application successfully. So this allows us to have multiple APIs under a single domain. And our gateway API can now act as a true API gateway. A slightly more advanced feature of the gateway API is the ability to modify request and response headers. This is using a special field called the request header modifier and response header modifier. What we can do with this is we can update request and response header fields. We can inject new headers or drop certain headers. This is exactly what something like CORS does. When the browser tries to protect the user from cross-origin API calls or cross-domain calls. As DevOps engineers, we often have to deal with CORS. Now, it's important to know at the time of this recording, we can manipulate request and response headers using Gateway API, but CORS is not part of the stable Gateway API implementation yet. Therefore, we can cover it in upcoming videos, but I can show you how to manipulate headers to bypass and work around CORS and show you the feature of manipulating headers. To show you the problem of CORS, what I've done is I've got a small web app that I'm going to port forward to quickly. So this simple web API is the example app we've deployed, the front end one, which makes an API call to example app.com to the Go microservice. When I click this button, this will attempt to make a JavaScript AJAX call, and you can see that it gets a CORS error. You can see this in the browser here. We're getting a CORS specific error. This is because localhost is not allowed to make an API call to example app.com. The browser is blocking it. Now, generally to deal with CORS, you would use a CORS module of whatever software you're using, and that should handle it. You generally never need to resort to custom scripting. But if you wanted to modify headers in HTTP requests, you can do so using the HTTP route. So here we're going to do it for the Go service, just so I can demonstrate to you what that looks like. We use the same route we had before. This time we still bind to the same gateway, same host name. We're going to keep the rules as we had it before. So we're going to keep our path matching, API/Go, go to the Go service upstream. This time we're going to add an extra filter. This is the response header modifier. And what you can do here is you can tweak response headers. You can either add or remove headers. So here we add headers, and you can provide any headers you'd like to add. This is just an array of names and values. So here I add the access control allow origin headers. I'm allowing localhost 8000 to make that call. I pass the methods we're allowed to execute. And that's pretty much it. That is how you modify response headers. And then I have my existing rule that I like to keep here, the URL rewrite, to pass any path path to our Go service. So I jump to my terminal and I apply that rule, and notice now on my web app I can click the button and now it's allowing it. And if we take a look at that network request in the browser inspection tool, we can see that it's injected these response headers. So that's how you manipulate HTTP request and response headers using the Gateway API. Now, Gateway API can also handle HTTPS. So think about things like TLS and SSL connectivity. So we can specify a TLS certificate in one specific area or wherever we like, and we can have HTTPS enabled, and all traffic coming into HTTPS we can either pass it through as is, but that would mean every microservice would need HTTPS support as well and would probably need the certificate reference. A lot of companies will terminate TLS at the gateway level. That means we don't need to pass the complexity and overhead of managing TLS at every service. Gateway API allows us to do this. In this video, I generated a test TLS certificate using a utility called MakeCert. You can find this utility on GitHub. It's useful for testing local environments. You can create a locally trusted development certificate that works in the browser that the browser trusts. It allows you to install root certificates, create a certificate, and then have it automatically accepted and trusted by the browser. Great for local testing. So I ran a few commands locally using curl to get the latest version of MakeCert, add it to user local bin and give it execution permissions. Then I set this environment variable of where I want my CA root to live. So I just put that in a specific folder. You can do this for Linux or Windows. I go ahead and run MakeCert and generate some certificates. And then I run MakeCert install, which allows me to install the root certificate in my local browser and trust it. With the TLS certificates generated locally, I can then deploy my secret to Kubernetes. So I can say kubectl create secret TLS, just like a real certificate. I'm going to call it secret TLS. I'm going to put it in the default namespace, and I will just give it my cert and key. Go ahead and punch that into the terminal, and now I've got a TLS secret created. Now, to enable TLS, we need to do two things. Firstly, we need to adjust the gateway to enable TLS as a listener. Listener allows us to bind to specific ports, such as 443. We then need to update our HTTP route to tell it to bind to the HTTPS listener, the new one that we'll be adding to the gateway. So on the gateway, I've already done this. I do have this endpoint called HTTPS. This is my new listener. Here I specify the port to listen on. So this is the port that the traffic will come in on for HTTPS. I'll specify mode as terminate. That means I will terminate TLS at the gateway level. And here is the certificate reference. I've now created that certificate as a secret in the default namespace. So the warning on the kubectl describe on this gateway should disappear. So that's the gateway. You go ahead and update your gateway after making these changes, and then you go to your HTTP route and update the reference to say you now want to listen to the HTTPS listener on the gateway. We keep the host name the same, and everything else, such as the rules, all remains the same. So two things to keep in mind. First, adjust the gateway to enable the TLS listener first. Enable 443, then apply the TLS listener in your HTTP route. Then we can go ahead and update our HTTP route. And one thing we'll need to do also is now port forward to our gateway API using 443 instead. So I'll just switch out the port forward in the terminal to 443 from 80. And the result of this is now we can go to HTTPS on the same URL, and this will route internally to HTTP on the Go service. Remember, the Go service does not have TLS enabled, so we're offloading at the gateway level. So I click that endpoint and you can see now my site is secure. So I have a locally browser trusted certificate here, and this is coming now over TLS. Another point of interest I wanted to make is a new feature called infrastructure labels. This is a useful feature because it gives us the ability to customize infrastructure under the hood for gateways. Think of cloud load balancers like AWS, ALBs, and Azure load balancers. You can use infrastructure labels to make changes to these. This is equivalent of an ingress where you set annotations or labels on infrastructure like services, and the cloud will go ahead and make changes to the load balancers under the hood. So this is all possible using Gateway API now. So it's important to know that everything we've done so far should be supported by any Gateway API controller. So from this guide, you'll have the knowledge to go ahead and look at something like Istio or Envoy or Contour or Kong or Traffic, and then you should know how to implement Gateway API features from a basic standpoint. At the bottom of this guide, I have a reference to Gateway API controller guides which I'm working on, which includes things like Traffic, Istio, Envoy, and it can include more. But I need you guys to let me know down in the comments what you'd like to see and what is it about that Gateway API that you're interested in, and some are subject to change. So that is the introduction to Gateway API. Let me know down in the comments below what sort of Gateway API controller and implementation you're interested in. And if you've been using Gateway API, what is your feedback so far? And more importantly, why are you interested in a specific controller? What are the things that help and what are some of the challenges? Let me know in the comments down below. And if you like this video, be sure to like, subscribe, hit the bell so you know when the next episode drops. And also remember to check out the development of the Ultimate DevOps Roadmap in the link down below, and follow on Instagram for more updates on the roadmap. And as always, thanks for watching, and until next time, peace.